There is something inside every particle of your body that has been carrying angular momentum since the universe was 3 minutes old, and nothing about it is moving. Physicists call it spin, because when they found it 100 years ago, the only picture that fit was a small ball turning on an axis. Then someone did the arithmetic. For an electron to carry the amount of angular momentum we actually measure, the surface of that ball would have to travel many times faster than light, and nothing with mass ever reaches light speed at all. So the picture died. The angular momentum did not. It is still there, it is conserved, it responds to magnets, and it has been measured to 12 decimal places, which makes it the most precisely verified quantity in the history of science. There is no axis, there is no surface, there is no motion of any kind, and this property, which nobody can picture and nothing performs, is the only reason you are resting on a surface tonight instead of sinking straight through it. Get comfortable and settle in. Hit subscribe if you're new here, because by the end of this, the floor beneath you will feel less like something solid and more like a rule the universe simply refuses to break. Now, let's slowly ease into this. Part 1. Everything turns. The planet you are lying on is turning, and it has never once stopped to ask your permission. If you are somewhere near the equator, the ground beneath you is moving at roughly 1,670 kilometers per hour, carrying you east through the dark, at something close to the cruising speed of a passenger jet. You cannot feel it, because everything around you is moving at the same rate, and because the turn is so smooth and so old that your body has never had any reason to develop a sense for it. But it is happening right now, and it will still be happening when you wake up, and the only reason you experience a sunrise at all is that this enormous rock is rotating you back into the light. Rotation is one of the few things in physics that seems to need no explanation. We grow up with it. A ball spins, a wheel turns, a coin dropped on a table wobbles into a blur before it settles. Children learn to spin before they learn to read. It is so deeply built into ordinary experience that it feels less like a phenomenon and more like a background condition of being an object at all. And when you look outward, the universe does not disappoint you. It turns out that almost everything out there is turning too, and much of it is turning far harder than anything you have ever seen. The sun rotates, though not the way a solid body does. Because it is a ball of plasma rather than rock, different parts of it are free to disagree about how fast to go around. Near its equator, the sun completes a rotation in about 25 days. Near its poles, the same rotation takes about 34 days. The sun is, in a very real sense, coming apart from itself in slow motion, endlessly, and has been doing so for 4.5 billion years without ever tearing. Galaxies rotate. Our own is a wheel of several 100 billion stars turning about a center, and the sun, carrying us with it, completes one lap in something like 230 million years. The last time the solar system was in the position it occupies now, there were no flowers on Earth. The dinosaurs had not yet finished arriving. But if you want to understand how seriously the universe takes rotation, you have to go somewhere much smaller and much more violent than a galaxy. There is an object in a globular cluster called Terzan 5, catalogued as PSRJ 1748, that holds the record for the fastest confirmed spin of any known object with a name. It is a pulsar, which is the collapsed core left behind after a large star has died and dropped inward under its own weight. It is roughly 24 kilometers across. You could drive from one side of it to the other in less time than it takes to watch a film, and it is turning 716 times every second. Sit with that number for a moment, because it does not survive being read quickly. Hold 1 second in your mind, not a measured second, just the ordinary length of one, the space between two heartbeats when you are resting, the time it takes to say a short word out loud. Now divide that second into 716 equal pieces. In each one of those pieces, an object the size of a city has completed a full turn. Every point on its surface has traveled all the way around and come back. It does that again in the next piece, and the next, and it has been doing it continuously, without slowing in any way you could notice in a human lifetime, since long before anyone existed to point a telescope at it. The surface of that object is moving at approximately 24% of the speed of light, nearly a quarter of the fastest speed anything can go, achieved not by a spacecraft or a particle accelerator, but by a dead star simply turning over. Let me take you there for a moment. You are floating a few hundred kilometers out, holding position, looking at something that should not be able to exist. It is a sphere, and it is not large. You can take it in with a single glance, a dark object the width of a small city hanging in front of you. It does not look like it is moving. At 716 turns per second, there is nothing for your eye to track. Any feature on the surface passes you far too quickly for your visual system to register, so the object presents itself as perfectly still, perfectly smooth, and completely silent. The stillness is a lie your eyes are telling you. In the time it takes for a single nerve impulse to travel from your retina toward your brain, that surface has gone around dozens of times. Its equator is outrunning light by only a factor of 4. Nothing you have ever watched turn, no drill, no turbine, no blade, is within 1,000,000 miles of this. And it is not spinning up or winding down. It is not in a process. It is simply doing this. And it will still be doing this, at very nearly the same rate, when the sun has burned out and gone cold. Now, none of this is mysterious. That is the important part. Everything I have just described is rotation in the plain, ordinary sense, and physics has known how to handle it for centuries. The quantity that describes it is called angular momentum, and it behaves in a way you already understand intuitively, even if you have never heard the term. Angular momentum depends on how much mass an object has, how that mass is spread out from the axis, and how fast it is going around. And crucially, in the absence of anything pushing on it from outside, the total amount of it cannot change. You have watched this law enforce itself. A figure skater spinning with her arms extended pulls them in tight against her body and speeds up dramatically without pushing off anything. She has not added rotation. She has taken the same amount of angular momentum and redistributed the mass carrying it, moving it closer to the axis, and the universe balances the books by increasing her rate of turn. When she extends her arms again, she slows. Nothing is created, and nothing is destroyed. The quantity is simply conserved, and everything else follows. This is also why the pulsar spins so absurdly fast. It did not start that way. It began as the core of a large star, perhaps 1,000,000 kilometers across, turning gently, maybe once a month. When the star died, that core collapsed to 24 kilometers. The same angular momentum, packed into a body 1,000 times smaller in every direction, has to come out somewhere, and it comes out as speed. The pulsar is a figure skater who pulled her arms in and never stopped. It is worth pausing on how completely this rule governs things, because it explains why the universe is full of rotation in the first place, rather than being a place where things mostly sit still. Consider how a solar system forms. You begin with an enormous, cold, ragged cloud of gas and dust drifting between the stars, hundreds of times wider than the system that will eventually come out of it. That cloud is not perfectly still. Nothing in the universe is. It has some small, accidental, overall rotation, the sum of every random drift and swirl in it, which will almost never cancel to exactly zero. Then gravity begins to pull it inward, and the cloud starts to fall toward its own center. And because angular momentum is conserved, that tiny initial rotation cannot be discarded. As the cloud shrinks, the same rotation is packed into a smaller and smaller volume, and the rate of turn climbs, exactly as it does for the skater. The cloud spins up, And because a rotating body flings material outward at its equator while nothing resists the collapse along its axis, the cloud flattens as it goes, until what began as a rough sphere is a disk with a growing star at the center. Every planet, every moon, every asteroid condenses out of that disk, inheriting its motion. That is why the planets in our system all orbit in the same direction, in nearly the same plane, and why most of them also rotate in that same direction on their own axes. It is not a coincidence or a design. It is one small, accidental rotation in a cloud of gas, conserved and concentrated over millions of years. A gyroscope makes the same point in your hands. Spin a wheel up, and the axis resists being turned, sometimes with surprising force, because changing the direction of that angular momentum requires you to supply a torque. The universe defends this quantity. It does not give it up easily, and it does not give it up quietly. So rotation is not something that happens occasionally in the cosmos. It is nearly unavoidable. Anything that collapses under gravity will spin, because whatever small turn it started with has nowhere to go. That is the world we grew up in, and it is entirely coherent. So here is where we stand, at the very beginning. Rotation is universal. Rotation is lawful. Rotation obeys a conservation rule we can write down in a single line, and the extreme cases are extreme only in scale, not in kind. The pulsar and the coin on the table are doing the same thing. And that is precisely the picture I am going to spend the rest of tonight taking apart. Because there is another kind of spin in the universe. It is carried by the particles you are made of. It shows up in laboratories as unmistakable, measurable, angular momentum. It responds to magnets, it obeys conservation laws, it can be measured to 12 decimal places, and it is one of the most precisely known quantities in all of science. And nothing about it is turning. Not slowly, not too fast to see, not in some hidden dimension. There is no axis, no surface, no motion of any kind, and the objects that carry it have no measurable size for anything to go around. The angular momentum is real, the rotation is not. Physicists gave this property a name in the 1920s, before they understood what they were naming, and we have been stuck with that name ever since. They called it spin. It may be the single worst chosen word in the history of physics, because the word makes a promise the universe does not keep, and generations of people have spent years trying to picture something that cannot be pictured because the label told them it was there. By the end of tonight, you are going to know what spin actually is. Not the metaphor, the thing itself, as far as anyone can state it. You will also know why it should unsettle you rather than merely puzzle you, and why the answer has almost nothing to do with anything turning and almost everything to do with the fact that you are currently resting on a surface instead of passing through it. But we are not ready for any of that yet. To get there, we have to go back to the 1890s, to a laboratory in the Netherlands, and to a very small problem with the color of light. Part 2. The light that split wrong. Every element in the universe has a signature, and the signature is written in light. When you heat a substance until it glows, and pass that glow through a prism, it does not spread into a smooth rainbow the way sunlight does. It breaks into a set of sharp, separated lines, a specific pattern of colors, at specific positions, with darkness in between. Sodium produces two closely spaced yellow lines. Hydrogen produces a particular red, a particular blue-green, a particular violet. The pattern never varies. Heat sodium in a laboratory in Berlin, or observe it in the atmosphere of a star 11 billion kilometers away, and you get the same lines in the same places, because those lines are produced by the internal structure of the atom itself, and that structure is identical everywhere. This was, in the 1800s, an extraordinary practical gift. It meant astronomers could determine what distant stars were made of without going there. simply by reading the barcode in their light. And it was also a standing puzzle, because nobody yet knew why atoms produced lines rather than a continuous smear. In 1896, a physicist named Peter Zeeman, working in Leiden, decided to see what would happen if he put the glowing substance inside a magnetic field. The lines split. Where there had been one line, there were now several, spread slightly apart, and the spacing depended on the strength of the field. It was a small, clean, reproducible effect, and it was immediately clear that it was telling us something about the machinery inside the atom. Hendrik Lorentz, Zeeman's senior colleague, produced an explanation in terms of electrons moving in orbits. A moving charge makes a magnetic field. A magnetic field placed inside another magnetic field feels a twist, and the energy of the atom therefore depends on how the orbit is oriented relative to the external field. Different orientations, different energies, different lines. Zeeman and Lorentz shared the Nobel Prize in 1902 for the discovery and its explanation. The explanation was elegant, it was correct as far as it went, and it did not work. It worked for some lines. For others, and there were a great many others, the splitting came out wrong. The number of components was wrong, the spacing was wrong, and no adjustment of the orbital picture could fix it. Physicists took to calling these cases the anomalous Zeeman effect, which is a polite way of saying the cases we cannot explain, and the name stuck for the better part of 30 years. Here is what made it so maddening, and it is worth being precise about, because this small technical detail is the first appearance of the thing this entire video is about. If the splitting comes from orbital motion, then the number of separate lines you can get is fixed by geometry. An orbit can be oriented in a certain number of distinct ways relative to the magnetic field, and quantum mechanics, even in its early, half-formed version, restricted those orientations to a discrete set. Work through the arithmetic, and you always get an odd number. 1 line, or 3, or 5, or 7, always odd. There is no way, using orbital motion alone, to produce an even number of components. And the anomalous cases were producing even numbers. 2, 4, 6. That is not a small discrepancy. That is not a measurement being slightly off, or a correction term being neglected. An even number, where the theory permits only odd numbers, means the theory is missing an entire source of angular momentum. And worse, it means that missing source is contributing in half units rather than whole ones. Half of something that everyone was certain came only in whole amounts. Nobody could say what was providing it. I want to make sure the shape of this problem is clear, because it is the hinge the whole century turns on. By the early 1920s, physicists had a working picture of the atom in which electrons occupy orbits, and those orbits are restricted. Not every path is allowed, only a particular set. Arnold Sommerfeld had extended the original picture to allow orbits of different shapes and different orientations, and the number of allowed orientations was fixed by a whole number. If that number is 1, there are 3 permitted orientations. If it is 2, there are 5. 3 gives 7. You will notice what those have in common. Every one of them is odd, and they are odd for an unavoidable reason. The orientations run from fully one way, through a middle position that points neither way, to fully the other. There is always a middle. The middle is why the count is always odd. An even number of components means there is no middle. It means the thing being measured has no neutral position, no way of pointing sideways, no option that sits between the two extremes. That is a very strange demand to make of anything that moves in a circle, and it was completely without precedent. Whole numbers had appeared all over the new physics. Energy came in whole multiples. Orbital angular momentum came in whole multiples. Everything that was quantized in whole units. Half a unit was not a smaller version of a familiar thing. It was a different kind of thing entirely. And yet the spectral lines were sitting there, in every laboratory in Europe, splitting into 2 and 4 and 6 components, and had been for a quarter of a century. The problem became genuinely notorious among the small community of people working on atomic structure in the early 1920s. It was the kind of problem that made careers and ruined moods. And the person it seems to have tormented most was a young physicist named Wolfgang Pauli, then in his early 20s, who would go on to become one of the most formidable and most feared minds in the field. A man whose critical judgment was so sharp that colleagues joked about the Pauli effect, the tendency for experimental apparatus to break simply because he had entered the building. There is a story about him from this period that has survived because it is so recognizable. A colleague came across Pauli wandering the streets of Copenhagen, clearly in a foul and distracted state, and asked him why he looked so unhappy. Pauli's reply was this: "How can one look happy when he is thinking about the anomalous Zeeman effect?" I like that story more than the physics sometimes, because of what it tells you about the texture of the moment. This was not a grand crisis with the fate of physics hanging over it. It was a specific, technical, irritating discrepancy in the pattern of lines produced by heated metal in a magnetic field. It looked like a loose end. Someone would tidy it up eventually. What it actually was the first visible edge of a property that had no place in the physics of the time, that could not be built out of anything then known, and that would turn out to be the reason the ground holds you up. Nothing in the theory could produce half units of angular momentum. Something inside the atom was producing them anyway, and doing it consistently, in every laboratory, every time anybody looked. The next real advance did not come from theory at all. It came from an experiment in Frankfurt that was designed to test something else entirely, that very nearly produced no visible result at all, and that succeeded only because one of the two men involved could not afford good cigars. Part 3. 2 spots. In 1922, 2 physicists in Frankfurt built an apparatus to answer what they took to be a fairly narrow question, and got an answer to a question nobody had thought to ask. Their names were Otto Stern and Walther Gerlach. The idea was simple enough to sketch in a few lines. Take a small quantity of silver and heat it in an oven until atoms begin to boil off. Let those atoms escape through a narrow opening so they emerge as a thin beam, traveling in a straight line through a vacuum. Send that beam between the poles of a magnet, but not an ordinary magnet with a uniform field. Shape the poles so the field is deliberately lopsided, stronger on one side than the other. Then let the beam land on a glass plate and see where it hits. The reason for the lopsided field is the whole point of the experiment, so it is worth a moment. An atom with a magnetic moment behaves, in a magnetic field, a little like a compass needle. In a uniform field, a compass needle feels a twist that turns it, but no net push in any direction. In a field that is stronger on one side than the other, the two ends of the needle feel different pulls, and the needle gets shoved bodily, one way or the other. How hard it gets shoved, and in which direction, depends entirely on how it is oriented when it goes in. So the apparatus is a sorting machine. Atoms enter with their little magnets pointed in various directions, and they come out deflected by amounts that reveal which way they were pointing. Now, what should happen? The silver atoms are boiling out of a hot oven. There is nothing in that oven organizing them. Their magnetic moments should be pointing in every possible direction, completely at random, the way a box of dropped compass needles would land. Some point almost straight up along the field, and those get shoved hard one way. Some point almost straight down, and get shoved hard the other. But most of them are somewhere in between, tilted at 40 degrees, or 70, or 110, and they should get shoved by intermediate amounts. The prediction is therefore completely unambiguous. The beam should arrive as a single continuous band, a smear, dense in the middle, where the most common in-between orientations pile up, and fading gradually toward the edges where the rare, fully aligned atoms land. Every physicist alive in 1922 would have drawn you the same picture. That is not what the plate showed. Come into the room with me for a moment. It is Frankfurt, and the laboratory is cold, because Germany in 1922 is not a comfortable place to be doing physics, and the heating is not a priority. The apparatus has been running. Gerlach shuts it down and removes the detector plate, holding it up to the light to see what the silver has written on it. There is nothing there. The beam is so faint, and the quantity of silver deposited over hours of running is so small that the trace is invisible to the naked eye. Whatever the experiment has found, it is sitting on that glass in a layer too thin to see, and there is no obvious way to bring it out. Stern leans in to look, close over the plate. He is a postdoctoral researcher on very little money, and he smokes cheap cigars, the kind that are cheap because they are heavy with sulfur. His breath carries that sulfur across the glass, and the sulfur finds the silver and reacts with it and turns it into silver sulfide, which is black. The image develops in front of them, the way a photograph comes up in a tray. And it is not a smear. There are two marks, two distinct separated spots, one where atoms deflected fully one way have landed, one where atoms deflected fully the other way have landed, and between them, where the overwhelming majority of the atoms should have arrived, there is clean, empty, untouched glass. Nothing in between. Not a thinning out, not a dip. Nothing. Take a moment with what that means, because it is easy to let it pass as a quaint historical result, and it is not quaint at all. Those atoms came out of a hot oven in random orientations. Nobody prepared them, nobody aligned them, and yet not a single one of them arrived at an intermediate deflection. Every atom in that beam, without exception, behaved as though its little magnet had been pointing either exactly along the field or exactly against it, as though the option of pointing sideways, or at 40 degrees, or at any of the infinite orientations available to any ordinary object in three-dimensional space simply did not exist. If you did this with actual compass needles, you would get a smear. If you did it with tiny bar magnets, or gyroscopes, or spinning tops, or anything at all that you can hold in your hand, you would get a smear. Orientation in space is continuous. A thing can point any way it likes. Silver atoms cannot. There are two options and no others, and the atom picks one on the way through. Stern and Gerlach knew immediately that they had found something important. What they did not know was what they had found. They believed they had confirmed a prediction of the early quantum theory of the atom, an idea called space quantization, which held that the orbits of electrons could only be oriented in certain discrete ways. In their excitement, they sent Niels Bohr a postcard congratulating him on the confirmation of his theory. They were wrong, and the way they were wrong is one of the better jokes in the history of physics. The silver atom's outermost electron, the one responsible for the entire magnetic behavior of the atom, sits in what is called an s orbital, and an s orbital has exactly zero orbital angular momentum. There is no orbit to be quantized. The thing they were supposedly confirming contributed nothing at all to their result. Every bit of the effect they measured came from a property of the electron that would not be proposed by anyone for another 3 years, that had no place in the physics of 1922, and that neither man had ever heard of. They had built the first clean, direct measurement of quantum spin 3 years before quantum spin existed as an idea. They got the right answer, from the wrong cause, on a plate they could only see because of a bad cigar, and they mailed a congratulatory note to a man whose theory had nothing to do with it. Otto Stern received the Nobel Prize in 1943, in part for this work. Walther Gerlach never received one. The result sat there for 3 years, undeniable and unexplained. 2 spots, 2 values, never anything in between. Some property of the electron was contributing angular momentum. That property could take exactly 2 settings, and nobody could say what in the world it was. Then two graduate students in Leiden, who had not been asked to solve this, and were not senior enough to know better, proposed an answer that turned out to be geometrically impossible. Part 4. The Impossible Ball. George Uhlenbeck and Samuel Goudsmit were graduate students in Leiden in 1925, working under Paul Ehrenfest, and between them they made the leap that everyone senior to them had failed to make. Their idea was the obvious one, which is exactly why it took two people junior enough to say it out loud. If the electron is contributing angular momentum that does not come from its orbit around the nucleus, then perhaps it is producing that angular momentum the only other way an object can, by turning on its own axis. Not going around the nucleus, but rotating in place. A small spinning ball of charge, which would generate a magnetic field exactly as a spinning charged sphere should, and which would therefore behave in a magnetic field precisely as Stern and Gerlach had observed. They worked out how much angular momentum it would need. The answer came out to a specific, fixed amount, 1/2 of a quantity called the reduced Planck constant, written as h bar, which is approximately 1.05 times 10 to the minus 34th in the standard units. That number is so small, it barely registers as a quantity at all, but when you feed it back into the anomalous Zeeman effect, the half units appear exactly where they had been missing, the even splittings come out right, and 30 years of unexplained spectral lines fall into place at once. It worked. It worked immediately, and it worked everywhere. So they wrote it up, and took it to Ehrenfest, and Ehrenfest sent it off for publication. And then Hendrik Lorentz, the same Lorentz who had explained the ordinary Zeeman effect nearly 30 years earlier, then in his 70s, and one of the most respected physicists alive, did the calculation that anybody should have done first. If the electron is a ball of charge that is rotating, and it has to carry that particular amount of angular momentum, then how fast is the surface of that ball moving? You can do this yourself, in principle. Angular momentum depends on mass, on size, and on rate of turn. You know the mass of the electron. You know how much angular momentum it needs. So take whatever size you think the electron is, and solve for the speed. The trouble is the size. The electron is very, very small, and angular momentum falls off sharply as an object gets smaller. A tiny object has to turn absurdly fast to carry the same amount as a large one. Using the classical estimate of the electron's radius that was standard at the time, Lorentz found that the surface of the electron would have to be moving at many times the speed of light. Not close to it, not pushing at it, well past it by an enormous factor, and getting worse the smaller you assume the electron to be. That is not a difficulty to be worked around. Special relativity had been published 20 years earlier and was thoroughly established. Nothing with mass reaches light speed, ever, under any circumstance. The picture that had made the idea instantly comprehensible, the little rotating ball, was not merely unlikely, it was flatly forbidden. Uhlenbeck and Goudsmit understood immediately what this meant for their careers. They had, as far as they could tell, published something absurd under their own names at the very start of their working lives. They went to Ehrenfest to ask him to withdraw the paper. Ehrenfest told them it was too late. He had already sent it. And then he said something to them that I think is one of the kinder things any supervisor has ever said to a student. He told them that they were both young enough to be able to afford a stupidity. They were not being stupid. That is the point of the story. The angular momentum was real, the amount was correct, the predictions worked, and the only thing wrong with their idea was the picture they had attached to it in order to make it thinkable. They had the physics right and the image wrong, and it would take 3 more years for anyone to understand that you could keep the first and throw away the second. There is another man in this story, and he does not get a paper. Roughly 9 months earlier, in January of 1925, a young physicist named Ralph Kronig had exactly the same idea. The electron carries its own angular momentum. Same reasoning, same conclusion, months ahead of anyone else. He was visiting Tübingen at the time. He worked it out, and he showed it to Wolfgang Pauli. Pauli, the same Pauli who had been made miserable by these very spectral lines, who wanted an answer to this problem more than almost anyone alive, told him it was a very clever idea, but that of course it had nothing to do with reality. Kronig put it away. He did not publish, and 9 months later, 2 students in Leiden published the same thing, and their names have been attached to it ever since, in every textbook, in every lecture, permanently. I want to sit with that for a moment, because the weight of it is not really about credit. Pauli was, by any measure, one of the finest physicists of the 20th century. His judgment was so reliable that people brought him ideas specifically to find out whether they were any good. And on this occasion, on the single question he most wanted answered, presented with the correct answer by a young man who had brought it to him in good faith, he was confidently, dismissively wrong, and his confidence was sufficient on its own to remove that answer from physics for the better part of a year. He was not careless. He was not acting in bad faith. He was doing exactly what a rigorous person does, which is to look at a proposal, see that it entails an object rotating faster than light, and conclude that it cannot be right. That reasoning was sound. The conclusion was wrong, because the proposal was correct in a way that nobody had the equipment to see yet, including the man who was better equipped than anyone. Set that against Ehrenfest, who did not know whether his students were right either, and who posted the paper anyway, and then told 2 frightened young men that a mistake was something they could afford. One of those 2 responses cost a man his place in the history of physics. The other one put it there. So by the end of 1925, the situation was this. There is a property of the electron that carries angular momentum in half units. It has exactly 2 settings. It explains everything it was invented to explain, and several things it was not. It is called spin, because the only way anyone could think of it was as rotation. And it cannot be rotation, because rotation would require the surface of the electron to outrun light. Physics had a working description of something, and no idea whatsoever what that something was. It stayed that way for 3 years, until a very quiet Englishman went looking for something else entirely, and found that spin was not optional. Part 5. Dirac's Forced Hand. Paul Dirac was not trying to explain spin. It is important to understand that, because it changes what his result means. In 1928, quantum mechanics was 3 years old in its mature form, and it had a serious structural problem. It did not respect special relativity. The equation at the heart of it, written by Erwin Schrödinger, treated space and time on completely different footings, in a way that Einstein had shown 23 years earlier could not be right. For slow-moving particles, this hardly mattered, and the theory worked beautifully. For anything moving near light speed, the 2 great achievements of early 20th century physics simply refused to sit in the same room. Dirac set out to fix that, and only that. He wanted an equation describing the electron that behaved correctly under the rules of relativity. It was a technical problem in mathematical consistency. He was not thinking about spectral lines or silver atoms or Frankfurt. He found the equation, and when he looked at what he had written down, spin was in it. Not added, not assumed, not put in by hand as an extra term to make the numbers work. The equation, constructed purely from the requirement that quantum mechanics and relativity coexist, described a particle that necessarily carries intrinsic angular momentum, and it specified the amount, exactly 1/2 h bar, with no freedom to choose otherwise, and no adjustable parameter anywhere in sight. You cannot write a relativistic quantum description of the electron without spin. It is not that spin fits comfortably into such a description, it is that the description will not close without it. This is the moment where spin stops being a puzzle and becomes something colder and more permanent. Before Dirac, The honest position was that the electron has this strange extra property, and we do not know why it has it. After Dirac, the position is that any universe in which quantum mechanics is true and the speed of light is a limit, is a universe in which particles like the electron carry exactly this much intrinsic angular momentum. It is not an accident of how our electrons happen to be built. It is a consequence of the two deepest principles we know, taken together. The equation had one more thing in it that nobody had asked for. It admitted solutions with negative energy, mathematically valid answers describing states that seemed to make no physical sense. Most people would have discarded them as artifacts. Dirac took them seriously and concluded that they described a real particle, one with the same mass as the electron and the opposite electric charge. Nothing like that had ever been observed. He predicted it anyway, on the strength of the equation alone. In 1932, Carl Anderson found it in cosmic ray tracks. We call it the positron, and it was the first piece of antimatter ever identified. An equation written to reconcile two theories had, as a side effect, predicted the existence of a mirror image form of matter, and been right. That is the pedigree of the thing we are talking about. Spin is not a curiosity attached to the edge of physics. It comes from the same equation that gave us antimatter, and it comes from that equation unavoidably. Which brings us to the question that everything so far has been circling, and that I have been carefully not answering. We have established that the electron carries a fixed quantity of angular momentum. We have established that this is real, measurable, and demanded by the fundamental structure of physics. We have established that the rotating ball picture is dead, because the surface would have to outrun light. So what is doing it? If the electron is not turning, what is producing angular momentum? Angular momentum is, by every definition anyone had ever written down, a property of things that go around. It is mass, moving in a circle. That is what the words mean. The answer physics arrived at is the part that people are rarely told plainly, and it is the reason this subject deserves the word terrifying rather than merely difficult. Part 6. Nothing is turning. Here is the answer, stated as flatly as I can state it. The electron carries angular momentum. It is genuine angular momentum. It adds into the conservation books alongside the ordinary kind. It can be transferred. It produces a magnetic field. It responds to magnets exactly as angular momentum should. If you take a rotating object and let it interact with an electron, the totals have to balance, and they do. And there is nothing rotating. There is no axis. There is no surface. There is no motion of any kind. Nothing is turning. I want to be very clear that this is not a way of speaking, or a simplification for a general audience, or a placeholder for something more complicated that specialists would phrase differently. The electron, in every experiment anyone has ever performed, behaves as a point. Scattering experiments, where you fire things at it very hard and watch how they bounce, have pushed the upper limit on any possible internal structure below 10 to the minus 18 meters. To give that a scale, it means that if any part of the electron is separated from any other part, that separation is smaller relative to a single atom than a coin is relative to the distance across the solar system. There is nothing there to go around, and so nothing goes around. The angular momentum is not produced by motion. It is not caused by anything. It is simply a property the electron has, in the same way that it has a mass and it has an electric charge. You would not ask what the electron is doing in order to have its charge. The charge is not an activity. It is part of what an electron is, and if you removed it, you would not have a slower or quieter electron. You would have something else entirely. Spin is like that. It is not something the electron does. It is something the electron is. And this is the point where I have to tell you something about your own mind, rather than about physics. You cannot picture this. Not because you have not studied enough. Not because the mathematics is beyond you, or because you would need a degree, or because the explanation has been badly phrased and a better one would let it click. There is no correct mental image of quantum spin, not a difficult one, not a partial one, none. Every physicist who works with this every day of their professional life is in exactly the same position as you. They can calculate it perfectly, predict it to 12 decimal places, build machines that depend on it, and they cannot picture it either, because there is nothing there to picture. The reason is worth stating carefully, because it is easy to hear this as a failure, and it is not one. Your visual imagination is a piece of biological equipment that was built over a very long time to model the behavior of objects at the scale of your own body: rocks, water, animals, things that have edges and positions and sizes and that move from one place to another. It is superb at that. Every intuition you have about how things behave is a compressed record of several 100 million years of ancestors successfully predicting the motion of medium-sized objects. Nothing in that history required your ancestors to model an electron. The equipment was never built for this, and there is no upgrade available. When you try to imagine spin and find that you cannot, you are not hitting the limit of your intelligence. You are hitting the edge of the format. The universe was under no obligation to be picturable. We simply assumed it would be, because everything we had ever met was, and spin is the point at which that assumption fails completely and permanently. So let me put the two halves of it together and let them sit next to each other without resolving them, because the discomfort is the accurate response. The angular momentum is real. It is measured to 12 significant figures. It shows up in your medical scans. It defines the length of a second. It is why magnets stick to your fridge. And nothing is turning. Those are both true, at the same time, permanently. And there is no picture in which they are both true. And there never will be. Now, before we go further, there is one more property of spin that has to be established, and it is stranger than everything I have told you so far. We know from Stern and Gerlach that when you measure spin along some direction, you get one of exactly two answers. Call them up and down, never anything between them. But notice something about that experiment. Stern and Gerlach chose the orientation of their magnet. They could have turned the whole apparatus on its side. If they had, they would have got two spots again, one up and one down, along the new direction. Any direction you choose, you get exactly two answers, fully aligned or fully opposed, and nothing in between. That already sounds impossible for an ordinary object. A compass needle pointing northeast is neither north nor east. It is genuinely in between, and if you measure it along the north axis, you get a partial value. Spin does not do partial. Whatever axis you pick, the answer is all one way or all the other. And it gets worse, because measuring along one axis destroys the answer along another. Take a beam of electrons and sort it so that you have only the ones that came out up along the vertical direction. You now know, with certainty, that these electrons are up. Send them through a second apparatus oriented vertically, and they all come out up again, every time, confirming it. Now take that same certain, sorted, definitely up beam, and measure it along the horizontal direction instead. It splits 50-50, half left, half right, at random, with no way to predict which any individual electron will do. Fine, you might say, that is a different question, and the answer is unrelated. But now take the half that came out left and measure them vertically again, the direction you already sorted for, the direction where you knew the answer with certainty. 50-50. The value you established is gone, not hidden, not merely unknown, gone. Asking about the horizontal direction did not just fail to reveal the vertical answer, it erased it. The electron does not carry a full set of spin values for all directions and reveal them one at a time. It has an answer for the question you actually ask, and asking a different question destroys the previous one. This is not a quirk of spin. It is the clearest and cleanest demonstration in all of physics that the properties of very small things do not sit there waiting to be found. But spin is where you can see it most starkly, with two outcomes and nothing else, in an experiment simple enough to draw on a napkin. It is worth being careful about what is and is not being claimed here, because this is the point where descriptions of quantum mechanics usually go wrong in one of two directions. The wrong direction, in one sense, is to say that the electron secretly has a definite spin along every axis, and that our measurement is simply too clumsy to read them all without disturbing things. That interpretation is comfortable, and it is what most people reach for instinctively. It is also ruled out. Experiments testing what are called Bell inequalities have established, repeatedly and with enormous care, that no such hidden set of pre-existing values can reproduce what is actually observed. The values are not there and being hidden from us. They are not there. The wrong direction, in the other sense, is to say that nothing is real until someone looks at it, or that human observation creates the world. That is not what any of this shows either. The apparatus does not need a conscious being attached to it. A measurement is any interaction that couples the spin to something large enough that the alternatives can no longer come back together, and the universe was doing that constantly for billions of years before anyone existed to notice. What is left, when you clear away both of those, is stranger and more disciplined than either. The electron has a definite spin along one axis at a time, and that is not a limitation on our knowledge, but a complete description of the situation. Asking about a different axis does not reveal a second fact. It puts the electron into a new situation in which the old fact no longer applies. There is no version of the electron carrying a full inventory of answers. There is only the answer to the question that was actually asked. And we are still not at the strangest part. There is one more property of spin, and unlike everything else tonight, it does not merely resist being pictured. It contradicts something you have believed about geometry since you were old enough to turn around. Part 7. 2 full turns. Take any object near you and turn it all the way around. A cup, a book, your own hand. Rotate it through 360 degrees, a complete circle, and bring it back to where it started. It is back. That is not a discovery. It is what a full turn means. A complete rotation returns a thing to its original condition. Nothing is left over. This is so obvious that it is difficult to even frame as a claim. And every person who has ever lived has taken it as given, because in the world of ordinary objects it has never once failed. Rotate an electron through a full circle and it does not come back. Something about its state has been inverted. Turn it through a second full circle, 720 degrees, all the way around twice, and only then does it return to the condition it started in. I know how that sounds. Let me first give you a way to feel that this is not as insane as it seems, and then tell you how we know it is true of real particles. The way to feel it is with a belt. Find one, if there is one nearby, or picture it clearly. Hold it flat, one end in each hand. Now, keeping the left hand still, rotate the right end through one complete turn, 360 degrees, and then bring your hands back close together, without letting go of either end, and without turning either hand any further. The belt has a twist in it. You cannot get it out. Move your hands around each other however you like. Pass one over the other. Take the belt around and under. The twist will move along the belt. It will change position, but it will not vanish. The buckle end and the held end are the same way up as when you started, and yet the belt between them is not the same. One full turn has left a permanent mark on the connection. Now rotate the right end through a second complete turn in the same direction. You now have, by any sensible accounting, twice as much twist as before, which ought to be twice as bad. Take the belt and loop it around, pass the whole loop over the buckle end, and the twist comes out. completely. The belt lies flat. 2 full turns undo themselves. 1 full turn does not. You have just performed, with an object from your wardrobe, the exact behavior that distinguishes spin 1/2 particles from everything you have ever handled. It has other names. Dirac's plate trick, the Balinese candle dance, where a dancer holding a candle rotates her hand twice to unwind her arm, and they are all the same fact. Objects that are connected to their surroundings genuinely distinguish between going around once and going around twice. That is an analogy, and analogies prove nothing. So here is the measurement. In 1975, 2 groups working independently, one led by Helmut Rauch in Vienna, one led by Samuel Werner in the United States, decided to test the 720-degree behavior directly, on real particles, in a real apparatus. They used neutrons, which are spin 1/2 like electrons, and a device called a neutron interferometer. Come and watch this one, because it is the single strangest thing I will show you tonight. A beam of neutrons is traveling through a machine cut from a perfect crystal of silicon. The crystal splits the beam in 2, and the halves travel apart from each other along separate paths before being brought back together and recombined. This is the same trick that has been used with light for 2 centuries. When the 2 halves meet again, they interfere, and the detector reads out a pattern that depends exquisitely on what happened to each path along the way. If both halves arrive in step, the signal is strong. If they arrive out of step, they cancel, and the signal drops. Both paths are identical. The apparatus is stable, the crystal is cut to atomic tolerances, the beam is steady, and the detector reads a bright, constructive signal. Now a magnetic field is switched on in one arm. It is tuned very carefully, so that as the neutrons pass through it, their spins are rotated through exactly 1 full turn, 360 degrees, around once, and back to where they began. Nothing else about the apparatus is touched. The path length does not change. The neutrons are not slowed or heated or disturbed. They have simply been turned all the way around and returned to the orientation they had on the way in. The signal inverts. Where there was constructive interference, there is now destructive interference. The neutrons that went around once come back out of step with the ones that did not, by exactly half a cycle, the signature of a state that has been multiplied by -1. And when the field is doubled, so the spins go around twice, the signal comes back to where it was. That is a measurement. It is not a metaphor, and it is not an interpretation. Rotating a real particle through a complete circle, in a laboratory, using nothing but a magnetic field, physically changes it in a way you can read off a detector, and rotating it through a second complete circle changes it back. A spin 1/2 particle needs 2 full turns to come home. I want to make sure the full weight of that lands, because it is easy to file it away as a technical curiosity about neutrons. The rule that a complete rotation returns a thing to itself is not something you learned. It is not a fact you were taught in a classroom, and could in principle have been taught differently. It is one of the deepest assumptions your mind makes about what space is, so basic that you have never had occasion to examine it, and it is built into every motion you have ever made, and every object you have ever handled. The particles that you are constructed from do not obey it. Not in some exotic environment, not under extreme conditions. Right now, in your hands, in the water in your cells, in the iron in your blood, there are particles for which 1 complete turn is not a return, and it takes 2 to get home. You are built out of things that disagree with you about the shape of a circle. And still, none of this is the reason spin matters. Everything I have shown you so far is strange. The angular momentum with nothing turning, the 2 values and nothing in between, the measurement that erases the previous answer, the 2 full turns. All of that is genuinely bizarre, and all of it is genuinely true. But if that were all spin did, it would be an oddity, a thing you learn about, find remarkable, and set down. Spin is not an oddity. It is one of the load-bearing facts of physical reality, and the reason has not appeared yet. Before we get to it, I want to slow down for a while, because the strangest property in physics turns out to be something we use constantly, in ways so ordinary that almost nobody notices they are using it. Part 8. The thing you use every day. You have almost certainly relied on quantum spin this week, possibly within the last few minutes. Let me start with the one that puts it inside your own body. Imagine lying in a hospital, on a narrow padded bed that slides slowly into a tube. The machine around you is a magnet, and it is a serious one. A clinical scanner runs at 1.5 or 3 Tesla, tens of thousands of times stronger than the Earth's own magnetic field, and research machines go to 7 Tesla and beyond. It is quiet as you go in. The technician's voice comes through a speaker, telling you to stay still. What happens next happens to you, at the scale of your atoms. Your body is mostly water, and every water molecule carries 2 hydrogen atoms, and the nucleus of a hydrogen atom is a single proton, and a proton has spin. There are something on the order of 100,000 billion of them in an adult human. Ordinarily, their spins point in every direction, all disagreeing, averaging out to nothing. The field switches on, and a very slight majority of them take up alignment with it. Not all. The effect is tiny, a small statistical lean out of an enormous number. But there are so many protons in you that a tiny lean across that population is a real, measurable signal. Then a radio pulse comes in, at a very specific frequency. For protons, it is about 42.6 megahertz for every Tesla of field strength, and it tips those aligned spins over. And then it stops, and they relax back, and as they relax they emit. Your own body radiates a faint radio signal, produced by the spins of the hydrogen nuclei in your tissues returning to alignment. Fat relaxes at a different rate from muscle. Healthy tissue relaxes at a different rate from damaged tissue. Those differences are the contrast in the image. The picture the radiologist looks at is a direct readout of a quantum property of the atoms inside you. That is worth saying twice. The most unpictureable thing in physics, the property that has no mental image, that no one can visualize, that carries angular momentum without anything turning, is used routinely in every large hospital in the world to take photographs of the inside of a person's knee. The technique came from work by Isidor Rabi in 1938, and independently by Felix Bloch and Edward Purcell in 1946. Turning it into imaging was the work of Paul Lauterbur and Peter Mansfield, recognized with a Nobel Prize in 2003. Now let me give you a second one, which is on your wrist or in your pocket. Take a cesium atom. Its outermost electron has spin, and so does the nucleus, and those 2 spins can be aligned with each other or against each other. Those 2 arrangements have very slightly different energies, and an atom can flip between them by absorbing or emitting radiation at one exact frequency. That frequency is 9,192,631,770 cycles per second. It is not approximately that. Since 1967, that number has been the definition of the second, not derived from the rotation of the Earth, which is irregular and slowly getting worse. The international standard of time is a count of spin flips in cesium atoms, and every clock in your life, every timestamp, every scheduled thing is ultimately traceable to that count. Satellite navigation lives or dies on this. The satellites overhead carry atomic clocks, and a position fix is really a comparison of arrival times from several of them. An error of a few billionths of a second becomes an error of a meter or more on the ground. When your phone knows which side of the street you are standing on, it knows because cesium atoms flip spin at an utterly dependable rate. Here is a third, and this one is on your fridge. A magnet works because the spins of electrons inside it are aligned. Each electron's spin generates a small magnetic field, And in most materials, those fields point every which way and cancel out. In iron and a few of its neighbors, a purely quantum effect called the exchange interaction, which has no counterpart in classical physics at all, makes it energetically favorable for neighboring spins to line up. Enough of them line up over a large enough region, and the effect becomes something you can hold. A magnet stuck to a refrigerator door is quantum spin, aligned across billions of atoms, made large enough to see. And there is a fourth, which for a couple of decades held nearly all the world's data. In 1988, Albert Fert and Peter Grunberg independently discovered giant magnetoresistance, an effect in which the electrical resistance of a thin layered material changes dramatically depending on the relative alignment of spins in adjacent layers. That effect made it possible to read magnetic bits far smaller than anything before, and the hard drives of the late 1990s and 2000s were built on it. Fert and Grunberg received the Nobel Prize in 2007. The field it opened is called spintronics, and it is still going. There is a fifth, and it sits at the frontier rather than in the past. Some of the most promising designs for quantum computers use the spin of a single electron, trapped in a tiny structure in silicon or in a defect inside a diamond, as the basic unit of information. The reason is straightforward once you know what spin is. A quantum bit needs a property with exactly two states that can also exist in combinations of both at once, and that is precisely what a spin 1/2 particle offers, and what almost nothing else offers so cleanly. The two-valuedness that made the Stern-Gerlach result so baffling in 1922 is now a design feature. And there is a sixth, quieter one, which has probably touched every medicine you have ever taken. Nuclear magnetic resonance spectroscopy, the laboratory ancestor of the hospital scanner, is one of the standard ways chemists work out the structure of a molecule they have just made. Different atoms in a molecule sit in slightly different magnetic environments, depending on what is bonded to what, so their nuclear spins respond at slightly different frequencies. Read out that pattern of frequencies, and you can reconstruct how the atoms are connected. Essentially, every pharmaceutical developed in the last half-century has had its structure confirmed this way, by listening to the spins of its own nuclei. I find that list difficult to hold in my head all at once. The property that cannot be visualized, that no human being has ever formed a correct mental image of, is used to photograph the inside of a knee, to define the second, to confirm the structure of a new drug, to store data, and to build the first quantum computers. Let me finish this stretch with the one I find hardest to be calm about. A hydrogen atom is a proton and an electron, and both have spin, and just as in cesium, those spins can be aligned or opposed. The energy difference between those two arrangements is extraordinarily small, and when a hydrogen atom flips from one to the other, it emits a photon with a wavelength of 21 centimeters, at a frequency of 1420.4 megahertz. That flip is very rare. For any individual hydrogen atom left alone, the average weight is something like 10 million years. But hydrogen is the most common substance in the universe, and there is so much of it drifting between the stars that even an event that rare, happening across that much material, produces a steady radio hum that fills the sky. The prediction came from Hendrik van der Hulst, a student in Leiden in 1944, working under German occupation, at a moment when there was very little reason for optimism about anything. It was detected in 1951 by Harold Ewan and Edward Purcell. And because that radio wave passes straight through the dust that blocks visible light, astronomers could suddenly see the structure of our own galaxy, the spiral arms, the rotation, the shape of the thing we live inside and cannot step out of to look at. We know what the Milky Way looks like because of a spin flip that happens to a given hydrogen atom about once every 10 million years. So this is the position we are in. The property that cannot be pictured is measured to 12 decimal places, is used to photograph the inside of living people, defines the length of a second, holds notes to refrigerators, stored the world's data, and drew the map of our galaxy. It is not remote, it is not exotic, it is furniture. And we still have not said what it is actually for. Part 9. Let us put this together. Let me stop here for a moment and gather up what we have, because we have covered a great deal of ground, and the next stretch is the part that matters most. We started with rotation as the most ordinary thing in the universe. Planets, stars, galaxies. A dead star turning 716 times a second, with its surface at a quarter of light speed. All of it lawful, all of it conserved, all of it exactly what it appears to be. Then a small problem with spectral lines refused to resolve, and the resolution required angular momentum in half units, which orbital motion cannot produce. Then an experiment in Frankfurt found that atoms in a magnetic field arrive at two positions and never in between, which no ordinary object does. Then two students proposed a rotating electron, and the rotation turned out to require a surface moving faster than light, and the picture died while the physics survived. Then Dirac showed that spin is not an addition to physics, but a requirement of it, that quantum mechanics and relativity cannot coexist without it. Then we said the flat thing. The angular momentum is real, and nothing is turning. No axis, no surface, no motion, no picture, not now and not ever. Then we found that measuring it along one direction erases the answer along another, and that a full turn leaves a spin 1/2 particle inverted, so that it takes 2 full turns to come home, and that this has been measured directly with neutrons in 1975. And then we found that this unpictureable property is thoroughly domesticated. It scans your body, defines your second, sticks to your fridge, and mapped your galaxy. That is a strange enough collection of facts to end on. Most accounts of spin do end roughly there, with a shrug and an invitation to marvel. But everything I have told you so far is, in a sense, still just description, strange behavior, carefully catalogued. None of it is the reason spin is the most important property in this video, and none of it is the terrifying part. The terrifying part is what spin does, and it begins with a rule that sounds like bookkeeping. Part 10. The rule about sharing. Everything in the universe is one of two kinds of thing, and spin is what decides which. Take any particle and ask how much spin it carries, measured in units of h-bar. The answer is always either a half integer, 1/2, 3/2, 5/2, or a whole integer, 0, 1, 2. There is no third category, and nothing in between. Electrons, protons, and neutrons all carry 1/2. Photons carry 1. That difference sounds like trivial arithmetic. It is the most consequential distinction in physical reality. Particles with half-integer spin are called fermions. Particles with whole